Hi there. What's going to follow is a video introduction, philosophical discussion and professional formation on the mechanics, with especially focus on articulated bodies and computer simulation of mechanisms of practical use, such as, for example, the piston, something which we commonly find in engines. Now, who should watch this video? Well, this video is addressed mostly to young boys from years 8 onwards. Anybody who has ever been interested in motorcycles, have ever played with and liked possibly the Lego technique, or some call it inverting the two words, technique Lego, or the mechano, or things of this kind, which of course not by chance allowed to do articulated mechanisms, being its main feature, of course, contrary to the simple Lego, which doesn't allow at all to do articulated systems. This video should be, I think, is a must for those instead involved already in the mechanical engineering area, theoretical physics, or making video games with realistic physics, or something that at least looks realistic, just doing the ponytail in a video game for a certain character, or do the motion of wires, which normally are very difficult to deal with, and trying to bypass the problem by using just points connected by springs leads to certain problems which anyway would require some investigation, and for people who are not trained in this, it may be a great loss of time, stress. Since even today, by the far most used operating system is the Microsoft operating systems, of course, in the scientific and programming nerds area, it's Linux, but most people still today use the Microsoft operating system. I will try to do most of the things on that, but there are some advantages. For example, there is the Game Maker software which runs on Microsoft Windows. I'll show you some things in Matlab. Otherwise, we will default to using Octave, which is of course syntactically the same, but it has no interactive push buttons which can be implemented, and has some limitations on graphics, especially the three-dimensional graphics. Of course, one of the, no, maybe the main point where our present school system fails dramatically is the problem of prerequisites to do certain things, or to do self-teaching, autodidactism. Of course, we know that in a scientific area, or anyway also in programming, video games, even very simply, any human field, even if people usually don't say that, in any human activity, almost autodidactism is very important. But in the exact sciences fields, or fields where some creativity is needed, is incredibly important. And of course, often one goes to school, but the informations necessary to understand some or any of books which would lead to acquire professional and working knowledge easily and with fun towards a certain human activity, the prerequisites are not met. And one opens a book such as this and finds some hieroglyphic partial derivatives, and this is, what the fuck, I can't read it, it's a delusion. Well, we will solve this, because we will at least hint at the prerequisites, say where to find them. They are minimal, I think, minimal really, for operations, being able to do a derivative on a polynomial, very simple, and knowing what the partial derivative is of a function, knowing what a function is, what a vector is, but these things we will do very graphical, illustrative things. And those who instead want to, or young boys and want to address towards the mechanical engineering or theoretical physics or game making games, I mean, which at least shouldn't look physically realistic, should watch this video very carefully, because I put great effort in collecting this information in this very simple way on mechanics and this simulation. Very fine. For example, one of the main problems is that one opens up this book and finds some abstract partial derivatives here and thinks, no, that's too difficult, that's, so to say, university level, but fucking listen, exact sciences don't deal with human prejudices, don't they? So he looks up how this is performed for simple functions with cosine, and the polynomial like x squared is just very easy. And one has just to understand, become familiar with the notation and do it. And of course, remember that you shall do the derivatives with finite differences. So, very cool. Very fine. I will bring up the entire dynamics, starting from dynamics of the material point, completely from zero. Even if you are watching this video because you want to get more into mechanics and its simulation, because you already know it, I strongly suggest to follow also this introductory part, because I will use a deduction, a derivation of the laws of the motion of the material point, which is not the one which is usually, or as long as I know, only the way which is presented commonly on introductory books on mechanics. Here you can have an example. Because the way I will be doing this, the notations used and the whole approach used will make it extremely easy to progress to the other kind of mechanics which allows to deal with mechanical systems. So material points undergoing some own spring force which make them behave as just components of a system, but that system is more important than its component parts. Very fine. I hope it won't be boring. It won't be boring. Let's go. This is not going to be the usual academic and too much theoretical crap which you may find in many, if not most, of the books on introductory or also advanced mechanics, also called dynamics. It will be clear, very practical, also funny, I think. I will show almost everything directly also on the computer, and it will be very clear. We won't forget the main purpose, that simulations, to be able to implement a simple simulation. Very fine, so assume we know nothing of dynamics, but we know two things. One, that the simplest dynamical system which one can investigate is a point-like object with a sufficiently big mass found in something called an inertial reference frame. We know from Galileo's rule that all inertial reference frames are equivalent to each other, and from this we can say, in more trivial words, that any reference frame which is inertial is good for our investigation. Very fine. So let's take a quiet room as an inertial reference frame. We know that in this case it means that if an object of this kind, which we will from now on call a material point, is not subject to external forces, it maintains spontaneously its initial state of motion, whereas state of motion means its velocity with its direction and overall speed. Of course, the problem here is that there is gravity, but we know again from Galileo's rules that this is not a problem, because what gravity does is always the same. So if we let this fall 1,000 times, it will always produce the same effects, as long as it's measurable, as long as we can precisely measure positions and times, and we also know what kind of thing this should be. We know that gravity will act only on this direction. Assume we want a generic investigation. We know that let's don't care about gravity, but we know that anyway a point should describe a path in the space like this, a path, a generic path. Assume that we have done a measurement. The problem is that we have 3 dimensions, but this is not a problem, because given a position of a point in an initial reference frame, let's put it here for example, we know that it will have initial x position, an initial epsilon position, and an initial z position. Very fine, our point is here. Now let's call this position x0, which is a vector. We are going to use the same notation starting from now for all the time. In order to determine the 3 coordinates of a position, it's sufficient to have coordinates of the position from one shot. For example, take this wall here and another shot, such that it must be perpendicular with the previous shot. For example, another sampling of positions from that wall. These are perpendicular between themselves, and we know from orthogonal projections that this should be perfectly sufficient to reconstruct the path completely, because the intersection, as they are interpreted in orthogonal projections of these two, produces automatically also position on another hypothetical shot which is perpendicular to both this and this. So starting from 2 sampling datasets of positions xz and epsilon z, using for example a multi-exposition photograph, putting the 2 cameras, one here and one here. Of course that's sufficiently far in order to eliminate problems of perspective, or using lasers to project things on walls and then doing a multi-exposition photograph of the walls and some creative things. We can do these samples. Assume we have this position sampling and that we did them at regular time intervals. Of course the time intervals are the same, and we also assume that of course the z coordinate, for example, are nearly the same because they cannot change, but in all measurements there is some uncertainty. So z should be the same, the x epsilon of course not, because they are completely different data sets, although taken from the same point. And of course, the most important thing to remember that this must be labeled, because we also must take into account the time at which they were made, so that we aren't going to confuse the sample points. Okay, of course, you know that these points here must be connected on the z-axis. So assume this originally was a curve, that also this was originally a curve. But of course, one cannot take infinite samples. Doing this job here, we can isolate separately the x coordinates, z coordinates and y coordinates as they were taken in time. And of course, this will become a three-dimensional path. Here some problems arise because experimental data will tell us that sometimes the material point may also come back like this. Okay, so do some strange things, and we want a generic mathematical description of how these positions change in time. Very fine. How to construct this? Of course, we need a smooth analytical curve in order to be able to do some theoretical analysis on this motion by doing operations on functions such as the sum, subtraction, and division, and most importantly the derivative with respect to the time variable and the integral. For this we need this be somehow an analytical function. So we know something which was investigated not by chance by Newton himself: polynomial interpolation. We must be very careful. We don't have to interpolate these points. This is what we saw early. Of course, we don't have to interpolate these points, but separately the coordinate points as they have evolved in time. Assume we have had some sample points. We have done this job here. We have isolated. We have done a third table where we reported, for example, for the z we solved the problem doing the average. We have done a table where we have t, x, y, z. However, there is some uncertainty on this, and this. We chose the average values, we did multiple measurements, and so we have our three components. We graph this simple thing. We shall have some sample points at regular time intervals. Very fine. The samples separately on x, y, and z should have occurred, of course, obviously, at nearly the same times. Okay, so it's licit to trace this connecting curve on the t-axis. Very fine. We want an interpolating analytical function that interpolates these points, because we know that before measurement, anyway, outside measurement, somehow these points describe a continuous curve. But of course, the generic continuous curve is too vague for us. We choose the best and the most easily tractable thing. Well, this candidate is the polynomial, because we can find this K0, K1, K2, and so these coefficients in a way that our polynomial function will cross these points. Use separately polynomial interpolation for the three coordinate samples. What is outside interval in which we have been sampling is completely out of interest, and let's go. We are interested in a polynomial function which well interpolates the points between the first and the last time of sampling. What happens outside is completely out of interest. Completely, I mean. For example, we started from here and we ended the measurements here. We're interested as x vector as a function of t is really realistically interpolating the sample points here. But what happened hypothetically before or after, nobody cares. Of course, the simplest example is the parabola, which needs 3 points to be univocally identified. The parabola is a polynomial of this kind. It's a second degree polynomial. In the general case, we have an nth degree polynomial. So a computer program which, starting from these coefficients, draws the interpolating polynomial, looks like this. The problem is how to obtain these coefficients so that the polynomial actually interpolates these points. Well, we are not interested in this procedure because these polynomials will disappear from our attention soon. But let's concentrate on things. Of course, we could reconstruct these curves as they look on x, z and epsilon z and do this funny thing and do the graphs. But we are actually not interested in that because we only wanted a mathematical way to describe paths as they evolve in time, path of a point of course, so that we can perform some analysis on it. Let's establish a general way of indicating the interpolating polynomial. It's this one, because if I have a polynomial 1 for each coordinate on which I have been sampling the points positions, then I will have 3 different polynomials for 1. But since a position is a vector which has 3 components, so it has is x, y, z a vector, thus I will have 3 different polynomials. But of course only the coefficients are interesting, so I indicate them as vectors. This is a parametric curve, it's called a parametric curve, and okay, we can say that any possible motion of a point can be represented in this way as long as we have a very large number of a very high degree polynomial, ideally infinite. We can do any operation on these functions, and from now on we can start our investigation. This is called a vector valued function. It's nothing mysterious. It just means that there are 3 functions considered as one object, because I need all 3 positions in time. Okay, very fine. Now we can start our investigation, but let's see how this interpolating thing looks on the computer, because probably this is the last time we see these things, so we don't want to do a bad job. This is the concept of polynomial interpolation. Time samples usually are at regular intervals, but of course the polynomial interpolation works for generic intervals. 4 points of 5th degree. In a computer program we can represent the sampling things this way. We have sampled the x positions this way, because we have a table like this. Okay, we have plugged it in the computer, like reading a text file which reports time, x, y, z, and so after all we end up with an array this kind 2, because the time and the value of the position on the coordinate, and we will have 3 of these things, x, y, and z. Of course the polynomial interpolation must be done separately for each of the 3 coordinates, and very fine. The computer, the code would look like this, because we should have to do interpolation on all the three axes separately, and then we can trace the curve. Because since the polynomial is univocally identified by the coefficients which have been determined by the interpolation procedure, so we have our polynomial, we can evaluate it where we want, we draw the points, and we have our curve. And of course, since this is a polynomial expression, we can evaluate it anywhere. But be careful that doing this will be meaningful only between the first sampling time and the last. So polynomial interpolation is realistic only between first and the last sampling point. Outside it's not meaningful. Polynomial is defined even at minus infinite and plus infinite, but it's absurd. It's realistic only here. Actually, curves like this can be done by simple polynomial interpolation, because as this can go up, this can go down, this can go to 0, minus values. Convince yourself. We will do a little computer graphing. That any trajectory can be done as long as you have enough sample points and the degree of the polynomial with which you decide to describe this path is number of sample points you took plus 1. What we obtained here, the motion, the path of the particle as a function of time became this. A polynomial function. Of course, Newton didn't use this notation because he didn't have the personal computer. But we are starting to use modern notation because I'm trying to be simple. Okay, not the theoretical crap which even doesn't help to grasp it better. After this, any theoretical consideration will be very, very easy. You could read any book on the argument and understand it also. Polynomial degree n constructed from data epsilon. I have a path. I want to try to obtain the loss with which this path is done, is evolving, if this is a mass point. First thing comes to mind is, of course, I'm trying to make it a bit like a telenovela. Of course, I didn't know what Newton thought about this, but okay. The first study we can do an analysis of time variation. How this varies instantaneously. If I could take instantaneously small times, which in the practice I couldn't because my instrument could only furnish me position samples at big intervals. I interpolated with a polynomial, a smooth function. I want to do an analysis of very small t. I know. Actually, in the real nature how it works, I don't know, but on this analytical, artificially constructed function, I can do this. The rate of variation, which I call v as a function of time and indicate as ddt of x time, is what? Is t plus small dt min. This is a vector. I do this ratio. Now don't force me to write it, but consult any book on mathematical analysis, basic mathematical analysis, or in English often calculus, and look for derivative you will discover, and Newton invented that I had to do this operation. You discover that if this tends to 0, when you perform this operation on a polynomial, you obtain another polynomial. The time derivative, as we call it, of this is again a polynomial expression, but of degree n-1. Again, it depends on this data, because I construct it and then I derive it. Don't force me to invent new notations, please. You know, it's a polynomial. There is a rule to have it, and it's very simple. We discover this is the rate of variation in time of the position of the particle as it advances its motion. What we discover is that in the definition of the initial frame of reference, that when no forces act, the particle, the body of this kind, maintains its state of motion, means that this is constant. So we can already formulate that first Newton's law, doing that this is constant. But if this is constant, it means that its rate of variation is 0. Therefore, we define another thing, which is the time derivative of v acceleration vector equals the time derivative of vector v, which is again a polynomial obtained with that funny rule. First law we formulated, Newton's first law, acceleration, no forces act, equals 0. I don't think, if this is true, how can we construct the motion? Now, the inverse operation of derivation, we have an initial position x0 vector. So what's this? The inverse of the derivative is this. We indicate it like this. It's sort of integral. For a polynomial, it's again a polynomial. Of course, I did the constant, but we don't care about that. No, we assume that it's 0. We put it ourselves because I mean, x0 plus what? Integral of the velocity vector in t as a t. Look up what this operation means in one of those books, and calculus. That's all. Of course, this doesn't change, otherwise we should also understand how it changes. So first law Newton is we can do like this. The problem with acceleration, of course, second law of Newton says acceleration equals force vector divided by m. So we have, depends on t, but this is completely unknown. But okay, of course, force is applied to the particle locally, and it causes the acceleration to change to assume a proportional value, proportional with m, f divided by m value, which does in the same direction, but doesn't affect the velocity which it was having, and the position. This acceleration instantly dies as the force goes to 0, as expressed by this. Force can go suddenly, become very strong, and then stop. Force doesn't obey to any physical law. So we must only be able to construct from this and from the initial x0 and v0 the motion. force actually exists. Force is a given, like constants are given. From this we want to simulate the path which then this does, the predicted, given an initial position, of course. Rule: the velocity as function of time will be the initial velocity plus the integral of force vector divided by m. Since m constant, it can go 1 divided by m here out, but don't worry. dt, of course, in time, but this is quite obvious. It's of course also that maybe it's not a polynomial, but integrating, we can assume it is. It can be approximated with a polynomial, so also this is a polynomial. So, and with system with it, xt equals the initial position plus integral of vector vt. Okay, you see this is a system. This simulates material point dynamics. We plug it into the computer, which now I am going to turn on to show that to you with a game maker and so, or another software written in C or anything that this does. Very fine. Of course, if you plug this into this and you forget this, you get a longer expression, but we remain focused on this. Now a big question arises. We assume that the degree of the polynomial was n, but I cannot take a million samples, which the least n which allows me to do these operations. Well, the least n is when, for a very small time step, acceleration is a constant. Velocity, I integrate this. Velocity polynomial degree 1. Position degree 2. Least number, least n, 2. I can assume my xt is, if you have an acceleration which is inst divided by m, which is constant all the motion, very small time step, but this is constant, this is a inst. Velocity after a time dt is v then equals v before plus a inst per dt. Position then equals position before plus v then per dt. This done and repeated over again. Of course, we have intuition. At each repetition, I must check again what the force acting on the point is, and this way I will slowly construct a polyline, a motion in a three-dimensional frame of reference. Of course, the most important thing is to do a computer simulation with this. Very fine. This ends the dynamics of the single material point. I say again, single material point, which we used to call M or M1. This little procedure should suffice to do a computer simulation of this directly. Let's do the first example in GameMaker because it has incorporated graphics. In GameMaker, the procedure corresponding to this thing here is already separated, so actually all the main procedure which has to be executed, that is this one, is cast in a script called step. Because GameMaker is made like this, in a programming language like the C programming language, it would just look like this, so main procedure would be inside a while cycle because you put it there. C programming language, you would have all this block which shall be repeated because there is a while one infinite loop. The initial conditions would be, of course, in the same single main. Okay, but in GameMaker the initial conditions are put in one script here, obligatorily. Do you recognize these things? Cool. The step, which is corresponding to this thing, which is repeated all over again. Initial conditions executed once, and then it enters an infinite loop which is repeated forever again, and thus the step script and the draw script is repeated endlessly until one presses the ESC button. Of course, we had to choose units of measurement. Units of measurement, such as, for example, to use meters. We haven't been speaking about it, but the only obvious thing was that the units are the same on all three axes, because otherwise nothing would be univocous. Cause and effect, consequentiality would be violated because there would be missing informations, and the very operation of the derivative could not be done, could not have been done. Okay, this is reference frame. Now we say that when we write x0 vector equals a certain set of values, such as, for example, 1.345, these are meters. It means that when during the experimental data picking a number 1.000 appears, it corresponds to 1 meter of position from here. Mass equals 1 is 1 kilogram, and second for the time. So when t equals 1.000, it means 1 second passed since the 0 time, which is 0, which is the beginning of the data taking. Okay, let's run a simulation. We must have indicated the units, which is very important. Okay, we are trying to visualize directly this kind of thing. In the simplest case, to visualize the position of a material point in 3 dimensions, sufficient to propose separately an xz shot and then yz shot. So it's the easiest thing. After we will see also 3D visualization, we implement this. Then we will see it in 3 dimensions, but we first do it this way. Okay, this is the origo, and one grid corresponds to 1 units of measurement, which in our case is the meter. So 1 meter, 2 meters, 3 meters, and the same here in 1 meter, 1 meter, so 1, 2, 3, 1, 2, 3 meters. And with our simulation, this velocity is constant. After this brief introduction to the graphical visualization, we will focus on this procedure. Of course, in this little simulation the force was constant all over the time, but in fact here I put 3 dots saying that okay, the force may change. In the basic theory we have been introducing, we assumed that this, which is assumed to be a polynomial of some degree, like okay, n, like 4th degree, 5th degree, okay, but its dependencies in time, but we say that in the simplest possible case So for a very short time we can assume that this is constant. We have been assuming such kind of dependence and not such kind of dependence, which of course you could have written also this way, because this is simpler, because this has the same variable as the position, its derivative, and also the acceleration, which we have given some proper names. Of course these are vectors. We have given some proper names, but of course the name you use is quite arbitrary. At least for now it didn't have so much importance, as long as you were coherent with yourself. Very fine. Since this is time dependence, for us our discussion about polynomial things, this was the easiest possible assumption. But we can say that if we have such kind of simulation which goes time step by time step, here h tends to 0. In our initialization procedure we have h equals 0.01. It's a very small, you could have put also a much smaller value, but then the simulation wouldn't be so real time, it would be slow. But okay, it's something considerably smaller than 1, which in our case is a second, which is good. Very fine. In the introduction I didn't say it to avoid confusion, that this kind of force dependence, considering this instant by instant approach, this can be reconduced here, saying okay, now in the now instant, for example, imagine we are at the 100th simulation step. At each step it can evaluate, for example, there is a force depending on position, because for example we put a spring here, and this dependence would be force vector equals minus the modulus of this distance minus the rest length of the spring, which we could fix here, and the key constant and the direction of action, which is a versor, which indicates towards the end point of the spring, which is a conventional. Let's don't get too much into this. This is just an example. We'll show it just very quickly. This versor could be obtained by doing this instantaneous position vector divided by its length, which is this one. Okay, in this kind of dependence, if we do this evaluation of this force at every very close time step, from here we just quietly pass here, the simulation or assumptions works, this becomes a constant, and okay, the simulation works. So this is okay. Here is the folder. Now let's take the free endpoint better GFX game maker thing. We will find a graphics routine which is a little bit better and throws something like this. It throws exactly this thing. Okay, let's try it. X, Z, Y, Z, and X, Y. Game Maker may be confusing because of this user interface, but one positive thing is that we can say that all the physically significant simulation is cast in this script. And here I could have prepared for you any cool graphical routine. This is long and embarrassing. Or think of a three-dimensional graphical routine. All the physics is here. All the initial conditions are here. And of course, maybe some auxiliary variables are needed, like for the forces which come directly. Because, for example, I push the button, that must be summed to this, which is evaluated instant by instant here. Let's see a three-dimensional example. It's this one. This has interactive, and in the step procedure the positional forces are evaluated. Then an authentic Ft is taken as force interactive. And if there are also constraint forces or frictional forces, which has dependence on velocity, it's all summed here. Let's see. Change velocity. And as I stop to apply the force, acceleration suddenly dies and the velocity vector remains the same. See how it moves. There is some camera control. Or you can play around. You could, for example, add gravity force, classical gravity force, and a frictional force, which in the simplest cases x dot is often written as this, and this is often written as this thing, so don't ever get confused. This is evaluated instant by instant, so no problem. Try to simulate, for example, a ball reference frame with gravity, this frictional force, and you will see a realistic falling trajectory and so on. So this fully ends the dynamics of the single material point. The problem is how to extend this theory to the case when there are more points interacting. This way, if this didn't interact, the simulation would just be the same as this, but we would have to give an index to each of these and do the same procedure for each. We'd have to do it for M1, M2, M3, but that would be sterile. We must consider some interaction between these points and to understand the laws this interaction obeys to, because we seldom see a point-like thing. This is not point-like, and if it could be modeled as two material points connected by a very stiff spring with a very strong damping. Cool, but this exerts a force. The spring force is a positional force, sort of positional force. It depends on the relative distance between the 2 points in this line. Distance. Okay, let's consider there is a force that this point exerts on this, because there is a spring, or there is some field, like an electric field or something. Well, there is Newton's third law, which however doesn't introduce a new formalism. It says how these forces must be applied if there is some force which allows two material points to interact. Of course, here the problem is almost only of a definition, because an interaction force such as a spring put in between these 2 points. The question is to whether we consider it an interaction or as a force that one point just exerts on another without any regard to the means thanks to which it exerts this force. Okay, let's assume this who exerts what on whom approach. Let's say this is the jth material point. There is a spring or an electric field or something, let's consider a spring, thanks to which the jth material point exerts force on the ith material point. Very fine. The question is how to define this force. Okay, let's say that depending on how the jth point is distant from the ith point, the jth point exerts on the I point a force which I call Fji, which is, for example, the usual spring force or something, anyway, only dependent on this distance. The problem is that if I did only this, it would be like this didn't feel any force, and this remained with its inertial motion with no forces acting, and this instead felt the force depending on this distance. Regardless of the type of force, the only assumption that of course it's a force depending on the distance between these 2 points. Very fine. Newton's third law says that this situation, this way, is not possible, because any means there is thanks to which the jth point exerts a force on the ith point, Newton's third law says that if this is true, then it's also true that the ith point exerts on the jth point a force of the same intensity, same direction, but opposite verse. Is it clear? So if this original force Ji used to point from the ith point towards the jth point, then the force that the jth point felt would be necessarily pointing in the opposite verse. So this would be minus Fji. The important thing is not to get confused. This is actually very important both for our thing mainly aimed at mechanical engineering and simulation and only classical physics, but actually this law here is very, very important for, as long as I know, all branches of physics, I mean modern physics, of course, because this is actually fundamental. In practice, trying to interpret this thing, it would mean that if there is an interaction of this kind between 2 material points, this interaction necessarily must be reciprocal. Let's party. Means that there aren't unilateral interactions. If there is some interaction, this interaction is necessarily reciprocal and follows this rule. The next step is to consider what happens when there are more material points. There are more material points and there is an interaction between or all of the pairs, or between only some of them, because for example I put a spring between the M0 and M1 and between M0 and M3, but nothing else. Okay, the important thing is that in this case Newton's third law must be applied according to the definition, and must just remember to apply it to all pairs. And when the force for all pairs has been calculated, one must sum up and find the total force acting on each of these points, and that would be the thing. You may be wondering which is a pairing procedure which doesn't miss any of the pairs and excludes, of course, the pairing of one point with itself. So, for example, jth point with jth point, which is like absurd. Very fine. A pairing procedure is this one here. This is the pseudocode following the C style thing. Of course, I take this. I start from the first point according to a conventional labeling I have done at the beginning of the investigation, and then I go from the first and I pair it with all the others, going from the zeroth, but which will be excluded, and then going. So of course I implemented a computer demo for this which does only this pairing, and of course I am going to show it immediately. I mean, Newton's third law is so important, it's not wasted time to. I thought it was not wasted time. I implemented exclusively this thing here. Okay, the code, we have in fact this thing here. Then here the if block, this green thing. There are some operations like drawing and writing, but then of course the operation is done, the other two blocks, so this one and this one are close, and what we have done is only this. Let's see the graphical representation, which I try to make as funny as possible. Here I use colors, but I will provide also a printf only version that goes immediately also Windows. Jth, ith. I hope you can see it correctly, I'm not certain. Of course, here you can also read the pair which is being made now. So, jth and ith. And in the graphical representation the 2 points are drawn. On the points there is no labeling, but you could add it by modifying the program. It's actually like this. Very fine. Okay. Of course, after having thus generalized, having defined how to apply Newton's second law and the little single material point simulation we have done to a system of more points, we can try to make some considerations on this. For a spring, for example, we would have to be just very careful with the conventions we use in order to apply correctly this rule. Because if we say that I have a force that depends only on the distance between 2 points, so I could say distance ij, but considering that whether ij or ji is the same, because the distance is independent from the ordering, it's just a distance. So in order to apply correctly some force of this kind, one would have to carefully consider and implement in a computer simulation this thing. An example is here in order to avoid confusion. Once this calculates how much is the force according only to the distance, one must determine the versor of action. So that would be, so to say, the direction, but it also must, since all versors have necessarily also a verse and don't define so only a direction, we should invent a convention, for example, that the versor will point only and always from j to I, in this case, so that it would go always like this. very fine, and then also consider correctly the sign of the force in order to be able to apply it correctly. We have this versor, which is a conventional verse and direction. We have the intensity to apply, and thanks to Newton's third law, we know how to apply it correctly. I strongly suggest you to try it to implement some little simulation with GameMaker with this, but now we shall go on without bothering with this anymore.